And I have the pleasure of introducing now a talk which is entitled Global Surfaces of Section for Reeb Flows in Dimension 3 and Beyond. And we will have two speakers. We will have Umberto Hryniewicz from the Federal University of Rio de Janeiro and Pedro Salomão from the University of São Paulo.
I would like to start the talk by discussing the statement of the classical Poincaré-Birkhoff theorem. And this is a statement about a homeomorphism of the closed annulus that preserves area, it preserves orientation, and it preserves boundary components. Once a lift is chosen to the universal covering, we can consider rotation numbers associated to the circle dynamics in both boundary components, the real value rotation numbers, denoted here by ρ0 and ρ1. And the so-called twist condition asks for these numbers to differ. When they're different, we say that the annulus map satisfies the twist condition. This is really a condition on the annulus map. It doesn't depend on the lift. And a somewhat modern version of the statement asserts that if P over Q is a rational number between ρ0 and ρ1, then there are 2 points in the strip, denoted here by capital P prime, satisfying these identities. This means that these points, when they get iterated Q times by the lifted map F, we land at the initial point shifted horizontally by the integer amount P. So in particular, these points project to periodic points of the underlying annulus map, but not only this, one can be sure that the orbits downstairs are actually distinct periodic orbits. And as a corollary, we get that the twist condition forces the existence of infinitely many periodic points. This statement is deeply connected to the origins of symplectic topology and to the origins of Floer theory. In the 60s, Arnaud realized that this statement was a corollary of a certain fixed point theorem for so-called Hamiltonian diffeomorphisms of the two torus, and then this observation led him to make the famous Arnaud conjectures, which then led Floer to develop Floer theory. So this is extremely, historically, for symplectic topologies, this is an extremely important statement. But Poincaré arrived at such a statement, or at a simpler version of the statement, by looking at celestial mechanics. He was studying the planar circular restricted three-body problem, and he realized that for certain energy regimes and small mass ratio, more precisely low energies, the dynamics after regularization, the dynamics of the satellite could be represented as a flow, as a Hamiltonian flow on a three-dimensional energy level, diffeomorphic to the three-sphere. And he used his continuation method to find two periodic orbits in this three-sphere. These periodic orbits, they formed a Hopf-link. But not only this, these periodic orbits, they were the boundary of an embedded annulus. And this annulus was a global surface section for the flow. This means that there was a well-defined return map, and this return map captured the whole dynamics of the energy level. And then Poincaré was able to verify, to check the twist condition for the annulus map, and then apply his result to find infinitely many periodic orbits for these situations of the planar circular restricted three-body problem. So here, the important non-trivial aspect here is that this annulus is a global surface section. Let me explain a bit more about what they are. A global surface section for a 3-space equipped with a flow is an embedded surface, compact, orientable, embedded surface, whose boundaries consist of periodic orbits for the flow, and for which all trajectories in the complement of these orbits hit the surface transversely and infinitely many often in the future and the past. In particular, you get the possibility of a two-dimensional reduction. You encode the dynamics as the dynamics of the return map, and this opens the door for two-dimensional methods. And that was exactly what Poincaré was able to do in the planar restricted circular three-body problem. This is an ideal situation for the dynamicist and also for the geometer, since two-dimensional methods are much more well-developed than three-dimensional methods. Let me describe one application of such a reduction. And before that, let me recall a theorem of Birkhoff, proved in the 1920s. It asserts that for positively curved geodesic flows on the two-sphere, there are plenty of such global surfaces of section. Every time you see an embedded closed geodesic, you can look at the embedded annulus on the unit sphere bundle, consisting of unit vectors pointing towards one of the hemispheres, and this forms an embedded annulus, and the assumption of the positivity of the curvature forces geodesic rays not containing the closed geodesic to change hemispheres infinitely many often. In particular, this means that this annulus is a global surface of section for the flow on the unit sphere bundle. The return map captures a lot of the geometry of the two-sphere, and I would like to describe this by one application, describing one application, which is an application to sharp systolic inequalities. So, in this particular situation, the total area of the two-sphere is encoded by the return map as the Calabi invariant, and up to a constant, and the number which is denoted here by L min, which is the length of the shortest closed geodesic, is just a spectral number of the spectral invariant of the associated generating function of the return map in case it exists. So both these quantities, the area and the length of the shortest closed non-constant geodesic, are captured by the return map, and one can use this dictionary between dynamics and geometry to prove this statement, which is in collaboration with Umberto Bonandolo, Barney Bramham, and Pedro, which asserts that if the Riemannian metric is sufficiently pinched, then we have this sharp systolic inequality, that the L min square is not greater than pi times the area, and this is sharp in the sense that equality holds if and only if the metric is all, if and only if all geodesics are closed and have the same length. So this answers a question that was raised by Babenko and clarifies the situation about systolic inequalities near the round geometry, and obtaining a sharp systolic inequality for all metrics in S2 is still a wide open problem. And here we clarify the situation near the round two-sphere. So that's an application of how, that's an example of how you can use the return map to study geometry. Okay, so let me go back to Poincaré and Birkhoff. So once you have a closed geodesic, you can consider so-called Poincaré's inverse rotation number, which is defined as the rotation number of the linearized dynamics transverse to the orbit. It is precise formula, like as it's written here. And putting together the statements of Birkhoff and of Poincaré-Birkhoff, we can prove the following result. If the curvature, or as a direct application of these results, if the curvature is positive everywhere, and if the embedded closed geodesic has transverse rotation number, or better said, inverse rotation number different than 1, then there are infinitely many closed geodesics. And the reason is that because the curvature being positive allows for the two-dimensional reduction, and inverse rotation number different than 1 implies that the return map satisfies the twist condition. So you put together the two results, and we get this statement. The reason why I stated this theorem is because in 2005, a strong generalization appeared as a result of work of Nguyen, which asserts that the same is true even if you don't have the two-dimensional reduction. Even if you don't have the global surface of section, the same is also true. Inverse rotation number forces the existence of infinitely many closed geodesics. These geodesics, they appear as satellites about the embedded closed geodesic. More precisely, for every rational number between 1 and the inverse rotation number, we have a PQ satellite, when the rational number is written in those terms as P over Q. I won't be specific about what is a satellite, but it's an example of so-called flat knot type, and it's enough to distinguish these geodesics. The idea, so the proof is very hard. It uses PDE methods. More precisely, it uses a parabolic PDE called curve shortening flow. And this flow has a special property that the length is a Lyapunov function. And using this variational structure, Nguyen constructs some kind of, he's able to implement some kind of Conley theory. For every such rational numbers, he produces, with this flow, he produces an isolating, so-called Conley block, an isolating invariant neighborhood with a non-trivial Conley index. And then the analysis of the curve shortening flow is enough to use this information to get the closed geodesic. So as I said before, this is to be thought of as a Poincare-Birkhoff theorem for flows, because it does not use the two-dimensional reduction. As strong as this statement is still, the class of flows for which it applies is somewhat still a bit restrictive, because it's just talking about geodesic flows on the two-sphere. And then I would like to describe a generalization of this theorem to a much larger class of flows, which is also going to be using PDE methods to study this flow, this ODE. But now we're going to replace this parabolic PDE by an elliptic PDE, so-called Cauchy-Riemann equations, and then use methods from symplectic topology to attack the problem of generalizing this to larger classes of flows. So I will more precisely consider Hebb flows on the standard contact three-sphere. So the setup here is standard symplectic space R4 with its standard symplectic structure, denoted here by omega 0. And I will single out this special primitive, lambda 0. And the contact structure on the three-sphere is given by the kernel of these one form. There are three important facts for us. Hebb flows of contact forms defining this contact structure are exactly the Hamiltonian flows on star-shaped energy levels in R4 up to time reparametrization. So this gives an idea of what kind of flows you're talking about. You're talking about Hebb flows on star-shaped energy levels. The second fact that's important for us is that the geodesic flows, they sit inside this class of flows, up to a double cover. And the third fact that's important for us is that when the metric is reversible, once you find an embedded closed geodesic, this lifting procedure will produce on the three-sphere a pair of periodic orbits forming a Hopf link. So we are here really talking about Hebb flows on the standard contact three spheres with a pair of periodic orbits forming a hop link. This encodes up to double cover all geodesic flows of, say, reversible Finsler metrics. So here's a hop link, very much like the situations encountered by Poincaré. So we are back to the situation of Poincaré, but now with no restrictions. Before making a statement, I'd like to recall the so-called transverse rotation number. Once you have a periodic orbit, you can look at the linearized flow, and this linearized flow on a transverse plane will induce a circle dynamics. So the space of rays issuing from the origin on this transverse plane is a circle, and the linearized flow defines a circle dynamics, and once trivialization is fixed, we get a real valued rotation number. For people used to Cohn-Lisinder indices, this can be recovered in terms of limits of Cohn-Lisinder indices. I mean, or precisely it's equal to the mean Cohn-Lisinder index. Okay. So the theorem that was joint work with between us and Almomin is this one. We consider a Hebb flow on the standard contact three sphere admitting a pair of periodic orbits forming a Hopf link. Let us denote by R0 and R1 the associated rotation numbers computed with respect to cipher framings. Okay. And the two real valued numbers. And the statement asserts the following. So before telling you what the statement is, let me just say that these two vectors, R01 and 1R1, they live in the complement of the third quadrant. They're vectors in the complement of the third quadrant. So they span a sector in case they span an open sector between them in case they're not equal. So in case they're not equal, if we choose a pair of relatively prime integers in this sector, in the open sector spanned by these two vectors, for each such pair, you find a periodic orbit in the complement of this Hopf link, which is distinguished, whose linking numbers with the components of the Hopf link are prescribed by these two integers. So PQ is a number in this sector, is a vector in this sector with integer coordinates, and you find a periodic orbit with these prescribed linking numbers in the complement. So let me draw a picture of the statement. Here's the statement again. We have these two numbers, these two vectors, 1R1 and R01. They span, in case they span a non-empty sector, for every pair of, for every point with integer coordinates, you find a periodic orbit with these linking numbers. In particular, there are infinitely many periodic orbits. In case we're talking about geodesic flows, reversible geodesic flows, the condition that holds different than one will be equivalent to saying that this sector is non-empty, so you get infinitely many periodic orbits there too. So here's a picture for the case when p is equal to 7, q is equal to 1. And as I said, the analysis behind this result is again, so the idea of the proof is again to explore the variational structure, but now we use the machinery of symplectic topology to somehow study the Morse theory of the action from classical mechanics. Okay. So again, it seems that one cannot really avoid somehow using PDE methods to find periodic orbits. It's a hard problem. Let me describe one application before I stop and Pedro continues. as we know from Grayson's work, the curve shortening flow preserves the property of being embedded. If you start embedded, you start with an embedded loop in the two-sphere, you flow it down by curve shortening flow, you stay embedded. And this allows one to do the following. The space of embedded loops in the two-sphere, say with a fixed Riemannian metric, modulo short ones, carries an obvious three-dimensional homology class. And then one can flow this class down and find a critical point, which is going to be then an embedded closed geodesic gamma, which satisfies this inequality. Since you're flowing down a three-dimensional homology class, you can be sure that Morse plus nullity is at least equal to 3, because 3 has to be should correspond to a generator in the local homology of these closed geodesic. In particular, from this inequality, we can be sure that the Poincaré's inverse rotation number is not smaller than 1, it's at least equal to 1. So in this case, there are two alternatives. Either it's 1, or it's strictly larger than 1. In the first case, we can then directly apply results of Nancy Hingston to this closed geodesic. In the case rho is equal to 1, one gets what's so-called a geodesic, in the language of Nancy Hingston, a geodesic which is not level nilpotent. And so such a notion was then put in the framework of symplectic topology by Victor Ginsburg in his proof of the Conley conjecture, but was already clear from Hingston's work. And in this case, one can then prove that there are infinitely many closed geodesics. This would be a very, very special critical point, and then Nancy Hingston's theory implies the existence of infinitely many geodesics, so it's a big step in this construction. And then if rho is bigger than 1, one can use Anguian's result, or independently our result, to provide infinitely many closed geodesics. So this is an independent proof of this classical statement by Bangert and Franks that Riemannian metrics on S2 have always infinitely many closed geodesics. But I would like to point out that if you're willing to push forward this program to the case of reversible Finsler metrics, then Anguian's result is not available, but also the first step maybe is not available. However, the step given by Anguian's result is then filled by our result. So the missing step to prove that reversible Finsler metrics have infinitely many closed geodesics is the first step. So that's one application I'd like to describe. I wanted to describe, and now I'll stop here, and Pedro will continue.
Okay. Thank you very much. So I will continue this talk in a very similar topic. Umberto talked about the use of pseudomorphic curves to obtain results in dynamics when we don't have a global surface of section, that version of the Poincaré-Birkhoff theorem. And, but I will go in a different direction, which is instead of defining invariants, these invariants, when they are non-trivial, they are used to detect periodic orbits. But here I will talk about some results using pseudomorphic curves to produce foliations for the flow. And these foliations eventually are used to produce periodic orbits and to extract some information about the dynamics. I will start with the type of problem that we are working now, which is about Hamiltonian functions on 4-dimensional manifolds, and the Hamiltonian has a critical value, and we analyze the flow close to that critical value. So let's assume that for energy equal to 0, this is a critical level, and there is a critical point that we see here, which has Morse index equal to 1, okay? And let's assume also that for energies below 0, the energy level contains 2 components that we see here to the left here. It has two components. And so since the Morse index of this critical point is equal to 1, when we go slightly above 0, the energy level now has only one component, which corresponds to the connected sum of these previous components below 0. Okay? This is a situation that we find very often when we are studying a Hamiltonian system with 2 degrees of freedom. For instance, if the Hamiltonian is of the form kinetic plus potential, and the potential has a hyperbolic saddle, then we have this type of critical point. And this type of configuration is very often found in physical chemistry and celestial mechanics. For instance, it might describe a chemical reaction. For low energies, we have these 2 components which correspond to the reactants and the products, and there is nothing essentially happening. But if you give energy to the system, then we have this situation, and now we find trajectories of the flow that are going from one side to the other. And exactly when it's crossing this region here, this neck region, it corresponds exactly the moment where the chemical reaction is occurring. Okay? I will consider the very simple case where these components are sphere-like, so they are 3-dimensional spheres. So this energy level above, for energies above 0 corresponds to the connected sum of 2 copies of the 3-sphere, which is again a 3-sphere. So everything here is a flow on a 3-sphere, and we would like to analyze the flow on this 3-sphere, which has this neck region here. Okay? Okay. To understand the dynamics on that energy level above 0, I will recall a very important theorem by Hofer, Vysotsky, and Zender for Hebb flows on the tight 3-sphere. And this theorem says the following. For a generic Hamiltonian flow, or for a generic star-shaped hypersurface in R4, or rephrasing it, for a generic Hebb flow on the tight 3-sphere, the flow admits a system of transversal section. What does that mean? A system of transversal section is a generalization of this notion of global surface of section. When we have a global surface of section, we have, in fact, an open book decomposition. Okay, and this system of transversal sections is a generalization of this notion. What does that mean? So this means that there are finitely many periodic orbits. The flow admits finitely many periodic orbits. They are called the binding orbits. And in the complement of these binding orbits, we have a true foliation. Okay. In the case of the tight 3-sphere, this foliation is not so complicated. Of course, every leaf of this foliation is transverse to the flow. It's a punctured sphere, so it has genus 0. And at each puncture, it is converging to one of the binding orbits. I will describe a little bit more. So the binding orbits have Conley-Zender index equal to 1, 2, or 3. There is this restriction in the Conley-Zender index of the orbits. I will describe this foliation a little bit better in the case we don't have index 1. So all the binding orbits have index 2 or 3. In the case the index is 2, the orbit is hyperbolic. In the case the index is 3, it may be hyperbolic, which reverses orientation, or it may be elliptic. Okay, so this is a very deep theorem. Of course, it's based on the study of pseudolomorph curves in symplectization, and they produce, in fact, a foliation in the symplectization of the 3-sphere, which is a 4-dimensional manifold. They solve this PDE, they find this family of pseudolomorph curves, and in the symplectization, it's a true foliation. And analyzing the algebraic properties of this foliation, they can prove that when you project the 3-manifold this foliation in the symplectization, it gives this system of transversal section with such nice properties. So I will put, as I said, I will describe a bit more of this foliation when we don't have a binding orbit with index 1, only index 2 and index 3. Then the foliation is quite simple, although it's not so simple. So the foliation has 3 possibilities for leaves, the regular leaves. The first one is a plane which is asymptotic to a periodic orbit with index 3. Okay? And whenever you have this leaf, it lies in a one-parameter family of such leaves. Okay? So the second situation is a plane, also a plane, but now it's asymptotic to a periodic orbit with index 2, which is hyperbolic. And when you have this case, this plane is rigid, it's isolated in the foliation. And if you have this plane asymptotic to this periodic orbit with index 2, you have a second plane asymptotic to the same periodic orbit, forming a two-sphere. Okay? All these regular leaves are transverse to the flow. Okay, so in this case, you have this two-sphere. And the third case of possible leaf is a cylinder, just a cylinder which connects an index 3 periodic orbit to an index 2 periodic orbit. These are the only possibilities for regular leaves in this foliation. So what is the simplest foliation which admits all such leaves? It is what we call a 3-to-3 foliation. This is an example of a system of transversal section which admits all those three types of regular leaves. So this foliation is as follows. It has exactly 3 binding orbits, and you can imagine that it has 3 binding orbits. You can imagine that these 3 orbits are concentric in the same plane, to simplify. And the one in the middle is the one with index 2, which is hyperbolic. And it admits this pair of planes converging to it. And it separates the 3 sphere into 2 regions, which are 3 balls. Okay? The bounded one and the unbounded one with the point at infinity. Okay, and then let's see what's happening inside these two spheres. It has this other binding orbit with index 3. There is a cylinder connecting the index 3 to the index 2 that we see there in green. Okay, to the left we see a cross-section of this foliation, and to the right we see a more 3-dimensional picture of the same foliation. And as I said before, associated to this index 3 orbit, inside there is a family, a one-parameter family of planes, which is parameterized by the open interval. And at the ends of this family, it's breaking. This family is breaking into a hemisphere associated to the index 2 orbit and that cylinder. In the other end of the family, it's breaking into the other hemisphere and the same cylinder. Okay, this is what's happening in the interior of this 2 sphere, and outside it's another copy of the 3 ball. It's happening exactly the same thing. It's just not in this picture, but there is this 3rd periodic orbit, again with index 3, and there is a cylinder connecting with the index 2 orbit, and this family of planes foliating the rest of the 3 sphere, okay? This is exactly what we call a 3-to-3 foliation. And so this foliation is predicted by this theory of pseudomorphic curves. And I would like to state a theorem related to that situation where we are crossing a critical level of the Hamiltonian function where we can see this 3-to-3 foliation appear. Okay, let's go back to that situation. The theorem, which is joined with Nayara de Paula, states the following. If the critical set, which is we see here in the middle, if the critical set here, which has 2 subsets, one in each side, that critical point is just a rest point of the flow, and if each one of these 2 subsets are strictly convex as a subset inside R4, as a hypersurface inside R4, then for all energies slightly above 0, WE, which is the energy level above 0, admits a 3-to-3 foliation. This is the first result that strongly uses pseudomorphic curves in symplectization. So since we are analyzing the dynamics of the energy level, it's important to say something about the dynamics, which is not only the existence of this foliation. And so we assume that the Hamiltonian is real analytic, is a hypothesis that helps us to prove this result, but maybe it can be avoided and assume only that it's smooth. And we can get as a corollary of this theorem that that energy level here contains infinitely many periodic orbits and infinitely many homoclinics to that hyperbolic orbit with index 2, okay? Let me describe a little bit more about this foliation. In fact, it's very well known by people who study, who are in the area of celestial mechanics, that when we have this situation here, this neck region contains a periodic orbit, which is called the Lyapunov orbit. And so this periodic orbit, curiously, it has Kohn-Lysander index equal to 2. And if we chop that neck region exactly in the middle, what we're going to see is a two-sphere. It's a subset of our three-dimensional energy level. It's a two-sphere, and if we chop it appropriately exactly in the middle, what we see is a two-sphere containing exactly the Lyapunov orbit, which is hyperbolic, and a pair of planes which are transverse to the flow. And this two-sphere contains one of the binding orbits of the foliation that we obtain. This is the P2, the Lyapunov orbit, and this pair of planes are part of the regular leaves of our 3-to-3 foliation. This picture represents the trajectories that are going from one side to the other. Here, in one of the hemispheres, it corresponds to the trajectories that are, for instance, going from the left to the right, and then this other hemisphere, it's exiting this three-ball here, bounded by the two-sphere. They are going from the right to the left. These are the transit orbits. In fact, in chemical reactions, the example that I said, this two-sphere is called the transition state, and this is exactly the moment where the reaction occurs, and the molecules, they get an intermediate configuration in between the reactants and the product. Okay, so this is the complete 3-to-3 foliation that I was saying, now with this representation outside that two-sphere. Okay, so let me just mention that this 2-3 foliation implies something about the dynamics, and as I said, this periodic orbit with index 2 that we see here is hyperbolic, and we see here also the local stable and the local unstable manifold of this hyperbolic orbit, which are cylinders emanating from it. Let's look at the piece of this stable and unstable manifolds which sit inside this three-ball. And so we can see that the unstable manifold intersects one of these planes, asymptotic to P3, okay? And the local stable manifold intersects these planes, but in this one parameter family, very close to the other end. And so we can use this foliation to push the local unstable manifold to the same leaf where the stable manifold intersects, more or less like in this picture here. So here is the local unstable manifold, and we use that foliation to push here. Maybe when it gets to the other leaf, it intersects the local stable manifold, but if it doesn't intersect, then the foliation forces it to come back here to the initial foliation, and we can repeat the argument. And since the area of each one of these planes is finite, and all of them, they have the same area, and the intersection of this stable manifold encloses a disk with a fixed area, we cannot have, we cannot avoid this intersections to never intersect this local stable manifold. So eventually, this foliation forces that the unstable manifold will touch the stable manifold and produce homoclinic orbits to the Lyapunov orbit. If we work a little bit more with the assumption that the Hamiltonian is real analytic, we can even prove that either the stable and unstable manifold coincide in that region, or if they do not coincide, then we can even show the existence of infinitely many transverse intersections between stable and unstable manifold, transverse homoclinies. There exist infinitely many of them. If they do not coincide, then this implies, in particular, that the flow has positive topological entropy. Okay, so I would like to say, to finish this talk, discussing a little bit more about an example in celestial mechanics, which is the Euler problem of two fixed centers in the plane. So you have two planets, which are the primaries, and we studied the motion of a satellite in the plane, which moves according to the usual gravitational law. It's attracted by these two planets. Okay? So the Hamiltonian function, which describes the motion of the satellite, we call the planets stay fixed. So this is called the Euler problem of two fixed centers in the plane. So the Hamiltonian, which describes the motion of this satellite here, is given by this expression here that we see in black. It's in fact very simple. It has a kinetic term that we see here, and there is a potential term that we see here. Okay? In red, we see a term that it doesn't exist in this example, but we have to add an example, a term like that, very similar to this one, which mixes position with momentum, if we want to study the restricted planar circular three-body problem. So when we add this term, which is sometimes called the magnetic term or the Coriolis force term, the dynamics gets much more complicated. In the Euler problem, when we don't have this term here, the dynamics is more or less well understood, well, very well understood, and this Hamiltonian is even integral. Okay, but when we add this term, it gets more chaotic. So this Hamiltonian has exactly that configuration that I said in the beginning. It has a critical value, and when you pass this critical value, two components of the energy level, they touch each other to form just one component. But here is an example. For low energy, it's the blue, it's the projected to the XY plane, the projection of the energy level to the XY plane here. This black dots corresponds to the planet. And here we see what happens with the energy level, the projection of the energy level when we increase the energy. Okay? This green corresponds to the projection for energies above the critical value. The critical value corresponds to this equilibrium point that we see in between the two planets. Okay? But here, this example, there is the usual problem in celestial mechanics. There are orbits which collide with the planets. So they collide in finite time. In fact, the energy level is not compact. It's unbounded. So we have to regularize, change coordinates to obtain a Hamiltonian for which the energy levels are closed. Okay, and this is done. There are very suitable coordinates, the elliptic coordinates, which transform this Hamiltonian into a new Hamiltonian, which is decoupled and integral. And the energy levels look like that. In fact, this transform is a 2-to-1 map. And now the energy levels get very simple. For low energy, this is the projection. There is no more singularity. There is no more collisions. For low energies, we have two copies of the trisphere, but since it's a 2-to-1 covering map, it's in fact an RP3 and RP3. And for energies above the critical value, it corresponds to the connected sum of RP3, of two copies of RP3. Okay? which is double covered by S1 cross S2. So the theorem, again with Nayara de Paulo, states that for all for energy slightly above the critical value, in the Euler problem, or two fixed centers in the plane, the energy level after regularization using elliptic coordinates admits this 3-to-3 foliation. Okay? So there is just one small difference, is that those families of planes converging to a periodic orbit with index 3, now to accommodate in this different topological setup, they are in fact converging to the double cover of a simple periodic orbit. This is the difference between S3 and connected sum of two copies of RP3. Okay? So we see this foliation. It's a different point of view of studying dynamics, and I would like to finish just saying that there is a conjecture that this foliation also exists in the planar circular restricted three-body problem for energies slightly above the first critical value. The dynamics in the three-body problem is very complicated, and this foliation, if it exists, would explain a lot of the numerical observations that are done in the three-body problem. Again, everything here, it's proved using holomorphic curves. We have to deal with a new situation of connected sum of RP3 with RP3. It's not the three-sphere anymore, where a lot of things are known. It's a new setup, so we have to rebuild the theory in this setup to prove this result, to prove the existence of this type of foliation. Okay, thank you.
We have two speakers, so we can ask twice as much questions, twice as many questions.
Who did formulate the conjecture?
We formulated the conjecture because we have a lot of evidences of that this holds there. But some steps in the proof of, at least in our way of proving this, they are not yet complete. And it's almost for sure that this foliation exists there, but I cannot say yet. Don't have a complete proof. So we formulated that. But it's based on the observations of other people. Hofer also had imagined that such a foliation would exist. Hofer, Vysotsky, and Zender. Maybe not exactly this rational 3-to-3 foliation where we have this double cover. Maybe a different foliation. But now, after understanding better what's happening on RP3 and connected some RP3 with RP3, we believe that this is the correct foliation that should exist there.
Just want to add that the reason why we formulate this conjecture, is because that would explain a lot of numerics that is not explained analytically.
So I made a mistake. We do not make twice as many questions, but every question gets 2 answers. Any other question? Do you have anything interesting to say about Finsler, non-reversible metrics?
Yes. If there are 2 pairs, so let's say in the 2-sphere, if there is a pair of closed geodesics, say in the same transverse isotopy class of lifts of embedded closed geodesics, of a lift and embedded loop in the 2-sphere. If you have two such geodesics and they satisfy a non-resonance relation, then there are infinitely many. That follows from the result in the first half of the talk. But of course, there are the talk examples where you have exactly those 2 and nothing else, and it's conjectured that there are 2 or infinitely many geodesics for any Finsler metric in a two-sphere. So this, so you get some partial results in the case you have this pair of orbits, as in the Katok examples, which are non-resonant. And but it's a tough conjecture. It's wide open, I would say.
Yeah, it's,
well, there are some genetic results due to Michael Hutchins and two collaborators, but in the degenerate case, it's still open.
So now answering in a different direction about foliations. So it's so for a generic flow on the tree-sphere, it's well known that there exists this system of transversal sections on the tight tree-sphere. The geodesic flow on the two-sphere lifts by a double cover, but we could try, it's still a conjecture, to find a foliation with similar properties directly on RP3, which is the unit tangent bundle of the two-sphere. We believe that a result such as that one of Hofer, Vysotsky, and Zender on the tree-sphere might hold also directly on RP3, maybe allowing some binding orbits which are multi-covered as asymptotic orbits of the leaves. But this is open and seems to be a difficult question to work directly on RP3, which would apply for Finsler geodesic flows.
More questions? Okay, then why don't we thank the two speakers again.